So, hi everybody. Thank you for the introduction, Patricia. It's a pleasure to be here. And first of all, of course, I'd like to thank the organizers for allowing me to speak here in this very nice workshop. I'm very thankful to be here, and I'm sure that the topic of the workshop will provide many interesting features for the future. And today I'm going to talk about a couple of joint works with my supervisor, David Pérez García from Universidad Complutense de Madrid, and a collaborator, Angelo Lucia, who was before in Copenhagen and now is at Caltech. And well, as Patricia said, we are going to talk before about quantum conditional relative entropy, and we'll use that to prove results of quasi-factorization of the relative entropy. The references are these ones. So, well, more or less the structure of the talk is going to be this one. So first, I'll introduce the motivation, why we are interested in this result, because I think it's more interesting to know why we care about this kind of results than the result itself. So in the second part of the talk, I will go to the result, and in the final part, we will see how these quasi-factorization results can be applied to quantum many-body systems. Well, so let's start with an open quantum many-body system. So we have a quantum many-body system that is contained in an environment, and it has unavoidable interactions with this environment. So we say that they are weakly coupled because these interactions have to be taken into account, but they are quite weak. And when these things happen, we can model this coupling of the system with the environment, but something that is called the Markov Approximation. So what does it mean? We have these kind of systems that are interesting for information processing. This is why we consider them open. Then the dynamics of the system, once it is initiated in a very specific state, is going to be dissipative. And we will model this evolution, this continuous time evolution, by a quantum Markov semigroup. We will see now what it is. So putting mathematics to this, we have a quantum spin lattice, which is nothing but a finite subset of CD. And to every side of this lattice, we associate a finite dimensional Hilbert space. We consider that all the Hilbert spaces have the same dimension, so capital D. And the global Hilbert space associated to the global lattice is the tensor product everywhere of the local Hilbert spaces. And once we have this, well, I said that this evolution can be modeled by a quantum Markov semigroup. And by this, I mean that this dissipative quantum system is a semigroup of completely positive trace-preserving maps, so quantum channels. And what this means for us is that if we have an initial density matrix and we let it evolve with time, we get something that we denote by rho sub t, and it's nothing but the exponential of time and one operator that is the generator of the dynamics, and we call Lindbladian. And this applied to the initial state, to rho sub lambda. And now we further assume several things on the system we are working with. So we know by some mathematical results of fixed point theorems that this system is going to converge. But what we have to assume is that there is just one equilibrium point, one equilibrium matrix, which is this thing that we denote by sigma. So if we just have one thermal equilibrium, this is necessarily going to converge when time tends to infinity to this density matrix, but we don't know anything about the kind of convergence. And in this situation, we can define something that is called rapid mixing, that says that, okay, we consider an initial state rho, we consider its evolution with time, which is given by this, and for any time, we consider the difference between the state at time t and the equilibrium state. And we take the trace norm of this difference and take the supremum over all possible initial states. Then this is going to tend to 0 exponentially with time, which is good, but the dependence with the system size may change depending on the situation. So we say that we have rapid mixing when this scales polynomially with the system size. And this is interesting, because these kind of systems have been studied in several fields, and they are, for example, they have interesting properties such as stability. When you perturb a bit the initial state, the way of converging is more or less stable. And they have also interesting applications as suitable devices for quantum memories. So we are interested in finding examples of systems that satisfy this rapid mixing property. And well, as always in quantum information, when you want to try to find examples of something happening, and you don't have a general strategy to prove in systems that these things happen, you go to classical spin systems, you see what happens there, and then you try to do the same in the quantum setting. So this is what we did. And one way of proving that in classical systems is by means of something that is called the log-Sobolev constant. So you can see here that if you define this quantity, which is like a bit strange, but you just have to take into account that the thing in the numerator is the derivative of the denominator. So then you have a quotient of something that here has a derivative of this, and then you take the infimum over all possible initial states, over all possible initial density matrices. This thing is called log-Sobolev constant, and when this thing is positive, for a certain Lindbladian the log-Sobolev constant is positive, you have this inequality just by integrating a differential inequality. And then you put this together with Pinsker's inequality, what you get is basically that the one norm of this difference can be bounded by this term here and the exponential of minus one constant and time. And this term here can be seen in several situations to scale polynomially with the system size. So it can be seen to be an example of this situation. So then, what can we see here? That if we have a positive log-Sobolev constant, then we have rapid mixing. So the problem that we had before of trying to find examples of rapid mixing can be translated to finding positive log-Sobolev constants. And now again, we can go to the classical case and see what the authors did for classical spin systems and try to do the same for quantum spin systems. So I'm writing now here the result in the classical case, and I know that the notation may be a bit awkward, but you just have to take into account the idea, not the notation itself. So the idea is that if you consider for a certain probability space the entropy of a function that is given by this measure of the function and logarithm of the function minus this term here, the measure of the function and logarithm of the measure of the function, which is how we usually define the entropy in the classical case, one can define for a sub-sigma algebra of the initial sigma algebra the conditional entropy just by conditioning every term to the sub-sigma algebra. And when you do that, in this classical paper in 2002, the authors got this inequality here, which says that if you consider two sub-sigma algebras that are not necessarily independent under the measure, you can bound the entropy of a function by the sum of two conditional entropies in these two sub-sigma algebras. And this term here measures how far these sub-sigma algebras are from being independent under this measure. So if they are already independent, this term is 1, and all this thing disappears. So now, this result is essential for them to prove examples of positive log-Sobolev constants, and hence examples of rapid mixing. So for us, if we were able to prove something similar in the quantum case, maybe we could have the same behavior in the system. And this is what we try to do in this work, okay? So the idea is that if you translate every term to its analogous in the quantum case, you get something like this. So here you have the relative entropy of two density matrices. Here you have an error term that we will see later how you can define. And here you have two things that is what we call conditional relative entropy. So the first thing that we have to do to prove something like this is to define these two terms, because we don't have the concept of conditional relative entropy in principle. And if you see the subindex here, the subindexes have an overlap. And this is how we are measuring that the previous sigma algebras of the classical case were not independent. So can we prove an inequality like this one? And the answer is yes, this is what we do in these works. So, well, if you got lost at some point of this explanation, don't worry. The only thing to take in mind is that we are going to prove results of this kind because they might provide interesting behaviors in quantum many-body systems. So now we go to the part where we talk about this quantum conditional relative entropy. And the first thing that we do is go to the relative entropy itself. And well, let me recall that this is the definition of the quantum relative entropy for two density matrices. And let me just highlight some interesting properties of the relative entropy because we are going to use them later during the talk. So first of all, the relative entropy is continuous with respect to the first matrix. It's additive, so if we put two product density matrices that are tensor products, then it splits properly. And if we just put a tensor product in the second term, then we have an upper inequality of the sum of the two terms with support in A and B. And finally, if we introduce a quantum channel inside the relative entropy, we always get a quantity that is less than or equal to the previous one. So these four properties of the relative entropy are quite interesting because of one thing, which is that they characterize the relative entropy. So if you have a function that satisfies the four properties, it necessarily has to be the relative entropy itself. And then we are trying to do something similar for the concept of conditional relative entropy, because we want to provide a concept that does the job of the inequality that we want to prove, but also it needs to make sense. So we are trying to do something similar. For that, we are defining a function that is continuous also with respect to the first variable. It's non-negative because in the classical case, the conditional entropy was non-negative, so the conditional relative entropy now has to be non-negative. And we also ask that it vanishes if and only if it can be recovered by means of the Petz recovery map for the partial trace. And this is for some recoverability purposes that we are looking for later. And also, well, you need to take into account that we are trying to provide, with this definition, with this conditional relative entropy in A, we are trying to provide the relative entropy of the global system, so of the system AB, conditioned to the fact that we already know the relative entropy in the complementary, so in B. So the idea is that if you put the two conditional relative entropies of A and B together, you should have the properties of additivity and superadditivity as you had before. So this is why we ask for just for the conditional relative entropy in A to have this property of semi-superadditivity, so to have an upper inequality with the relative entropy in A when you have a tensor product in the second term, and when you have tensor products in both terms, you just recover the relative entropy with the states with support in A. And finally, well, because of the idea that we want for the conditional relative entropy, it doesn't make any sense that if we introduce a channel with support in everything, that it decreases the quantity of the relative entropy. But what it makes sense, for example, is that if we introduce a channel just with support in A, it has to reduce the quantity because we are somehow studying the conditional relative entropy in A. So the idea now is that if you consider the conditional relative entropy in A and introduce a quantum channel and add here the effect that this channel has in B, which is given by this term, then it satisfies a data processing inequality. I know that this is a bit artificial, but it's something that is kind of reasonable. So we ask for this quantity to satisfy all these properties. And once we have this, well, we have a couple of interesting features, which is that the first one, considering the sum of the two conditional relative entropies in A and B, as I said before, it's continuous, it has properties of additivity and superadditivity. And of course, it doesn't have the property of monotonicity, because otherwise we will go to this characterization and then we will have the relative entropy, and we don't want that. And after that, what we saw was that with the properties that we were asking for, we only have one possible definition for conditional relative entropy, which is good, because then we are axiomatically defining this concept, and we don't have space to have a different definition for this concept, so that's interesting. And the only possible definition for this conditional relative entropy is given by this, by the difference between the relative entropy in the global system and the relative entropy in the complement. So once we have this, remember that we were looking for this concept to define, to prove a result of this kind, to prove an inequality of this kind. So now the question is, okay, you have defined this concept, are you going to be able to prove a result of this kind? And the answer is yes. So we consider a tripartite system, ABC. We put AB in one part and BC in another part. And then, with these definitions of conditional relative entropies, we prove an inequality like this, which gives you an upper bound for the relative entropy of the two density matrices in terms of the sum of the two conditional relative entropies, and this term that measures how far sigma is from being a tensor product between A and C, and is given by this difference here. And if you compare it to the classical case, you see that the idea is exactly the same. So you are replacing relative entropy by entropy, and here the same for the conditional relative entropies. And here this term was measuring exactly the same. So far so good. And now, well, you can rewrite the inequality that we have here if you replace the definitions of conditional relative entropies and by some elementary properties of relative entropies. You can rewrite the inequality that we had as this one. And this inequality is very nice, because if you recall the property of superadditivity, you had the inequality between the relative entropy of rho and sigma tensor product with these two relative entropies in A and B. And if you remember the property of monotonicity, you had this inequality every time that you consider a quantum channel. So now, if you consider first the partial trace in A and then the partial trace in B and put the two inequalities together, you get that twice the relative entropy is greater than or equal to the sum of the two relative entropies in A and B. So now you compare these two quantities, and you see that here, if this is a tensor product, you get a 1 here, and if it's a general density matrix, you get a 2. And what we have here is something in between. So it's something that when this term is less than 1/2, provides a better constant here than 2, and it's general, it's not just for sigma being a tensor product, and actually it's measuring how far sigma is from being a tensor product. So it's like a generalization of this property of superadditivity. And just let me briefly mention that this thing makes sense. And I mean that if you go to the classical case and consider the classical definitions, what we are providing here really extends the classical definitions, because otherwise, if you consider classical states and your definitions don't reduce to the classical definitions, you are like losing the you are losing much information in the way. So in our case, they do. After considering several operators, we can see that they reduce to the classical definition, so this is reasonable. And I'm going to skip the proof of the result, because I prefer to mention something about the applications of these results to quantum many-body systems. So now if we go back to the first part of the talk, you can remember that we wanted to prove positive log Sobolev constants. And in the classical case, they used these results of quasi-factorization of the entropy to prove that some log Sobolev constants were positive. And we wanted to do here something similar. So the idea is, now, given a certain Lindbladian, can we prove that the log Sobolev constant associated to this Lindbladian is positive using this kind of results? And well, the answer is not direct, so it would be very nice to say yes directly, but actually it's very difficult to prove that log Sobolev constants are positive in general in information theory. So we try to follow the same strategy that they followed in the classical case. And well, this strategy is based on 3 facts. The first one, I already said, that is the result of quasi-factorization of the relative entropy, which we already have. The second part just is based on defining a new thing, that is the conditional log Sobolev constant. So they had the log Sobolev constant. It's just defining something that is conditioned to a subregion. We'll see later how. And then if you're able to provide a lower bound for the log Sobolev constant of the global system in terms of a conditional log Sobolev constant, and you are able to prove that this conditional log Sobolev constant is positive, you get that the global log Sobolev constant is positive. So this is what they do in the classical case, and this is what we try to do here. And we managed to do it for a very particular case. So what we do is to consider the heat bath dynamics, and with product fixed point. So this assumption is very strong, I know, but well, it's already something. And we're able to prove that these dynamics, with this assumption on the fixed point, and the fixed point, I mean the thermal equilibrium that we were talking before about, so this sigma, this dynamics has a positive log Sobolev constant. And the heat bath dynamics is just something that is defined like this. So the global Lindbladian in the whole lattice is defined as the sum of the local Lindbladians in every site. And each one of them is defined as the difference between this term here and the identity. And this term here is nothing but the Petz recovery map for the partial trace in the complement of X. But the thing is that it's denoted by this because it's the dual of a conditional expectation, so it's just some notation. But the idea is that in this particular case, because of sigma being a product, you can, when you apply this conditional expectation, well, this dual of conditional expectation to a state rho lambda, you get the value of sigma in the site X tensorized with the value of rho in the complement. So it's interesting. You are just reconstructing rho in the site sigma, in the site X, and you are leaving it invariant in the rest. And for every site, you are considering the difference between this term and rho lambda, and you are summing everywhere. So this is the dynamics that we have here. And for these dynamics, first, we prove a result of quasi-factorization of the relative entropy. So now we just have an upper bound for the relative entropy in terms of the sum of the conditional relative entropies everywhere. And we don't have an error term here because sigma now is a product. And our error term was measuring how far it was from being a tensor product. So now it's measuring that it's already there. I mean, it's a tensor product. So this is why we just have a 1 here. And after defining a conditional log Sobolev constant, which is the same that the condition that the log Sobolev constant that we had before, but now we are conditioning to X both the numerator and the denominator. So when we define this, we are able to prove that the conditional log Sobolev constant is lower bounded by 1/2, which is something that is positive and is independent of the size of the system. And once we have this, putting it together with this result here, so this result here constitutes 0.1 of this scheme, and the other one that I just mentioned constitutes 0.3. So now we are going to provide 0.2, and then we get that we have the positive log Sobolev constant. So what we just do in this case, that is quite simple, this geometric argument now is very simple. We just have an inequality between the relative entropy and the conditional relative entropies. Because of the definition of the conditional log Sobolev constant, as the conditional relative entropy appear here, we can replace putting the conditional relative entropy here and the conditional log Sobolev constant here. We can replace the conditional relative entropies by these things here, and then just doing some algebra, we get the global numerator, so the one that appears in the log Sobolev constant. So now, taking the quotient between this and taking infimums, we get that the global log Sobolev constant is lower bounded by 1/2. So we get positivity of the log Sobolev constants. So now we see that our idea works, at least in this very particular case, but well, we are trying to extend it to more general cases. So of course the first question that one has is, well, you assume that your fixed point was a product. This is a very strong assumption. Can you drop it? So well, this is the huge open question of this part of this field, let's say. So the idea is to use the results of quasi-factorization that we showed before to prove more general log-Sobolev constants. And it's something reasonable to hold, because it's already proven that this heat bath dynamics with a sigma that is a more general density matrix, so not a fixed point, but the Giese state of a commuting Hamiltonian, this dynamics has a positive spectral gap. And the log-Sobolev constant is like an exponential improvement of the spectral gap. So if this is already true, maybe it's possible to improve it a bit to get a log-Sobolev constant. It's kind of reasonable. And of course, another interesting open problem is to see if this is the better definition that one can think about when one wants to define a conditional relative entropy, because you might argue that some of the properties that we introduce are a bit artificial or are too convenient for us. So maybe one can define it in another way that is a bit better. Well, thank you very much for your attention. Thank you for your questions.
Cool. Thank you, Angela. Are there any questions? That was a phone, not a man.
Hi, thanks for the talk. So could you go back to the slide where you introduced the conditional relative entropy and the properties that you wanted to have? So I was a bit confused. So you have, this semi-monotonicity condition. So you said that, there was a point where you said, well, we can't just ask for monotonicity because this is not what we want this quantity to capture.
Yes.
So my first question is, what exactly do you want the property, the quantity to capture? And the second is just on a formal level. So the second term, so this dB, is it a function on the density matrices on both systems? On AB? Yeah, no? I mean, that's how you define it.
You mean the thing that appears inside?
It just seemed like you're taking the trace from the two-system state, but then that's not how the quantity is defined.
Yeah, what you're doing here is applying first the quantum channel to rho, for example, and then you're tracing out the effect in A, so you are getting something that has support in B. So actually, this is just the way of writing it because of notation. But the idea is that when you have the conditional relative entropy in B of something that has support in B, as is this case, it's just the relative entropy of this thing. So putting here a B and not putting it is the same.
Okay.
But it's just because of the notation of the way of writing it, because you want it to be.
Thanks. And the first question?
And for the first question, so the idea of this conditional relative entropy is that we want to, with the relative entropy itself, we measure the distinguishability of the two density matrices in the whole system. And what we want now is something that measures this distinguishability in the global system conditioned to the effect in the complement. So the idea is because we are trying to extend the classical situation and also because of the thing that we want to prove afterwards. So this is more or less the idea that we want to get. So the thing is that if you apply a quantum channel, if it has support in A, so if it's just acting in A, it's reasonable that it acts the same that it would act for the relative entropy, just decreasing the quantity. But if you apply a channel that has support that is acting everywhere in A and B, you have to compensate the effect of this channel acting in B. So this is what we try to do here. So we get the effect of the channel everywhere, and we add the effect of the channel in B to compensate the effect.
Okay, yeah, I see. Thanks.
Okay, thank you.
Maybe one more very short question.
Are there some simple examples on channels where you can apply your machinery?
What do you mean, sorry?
Some examples of Liouvilleans where you can apply this easily, your stuff.
So, well, so far we just managed to apply to the heat bath dynamics. So just to
Okay, yeah.
to this Liouvillean here.
Yeah, well, I didn't mean some new examples, like even some old examples. Like if I take some local Liouvillean, is it very hard to compute these quantities? Like there's log Sobolev inequalities. Or
Well, it depends. For example, if you take the polarizing channels and you take the dynamics given by these depolarizing channels, it's very, well, it's not so easy, but there are some papers on that. It's already done. So if you take, for example, the polarizing channels with the identity as fixed points, these things can be computed. So it was already proven to have log Sobolev constants and all this stuff. But in general, it's not so easy to compute these quantities. So for example, for Davis generators of dynamics, this hasn't been computed. Thank you.
Cool. Well, let's thank Angela again.